connect to the screen and go in the presenter mode. Go in the presenter mode.
Yeah.
No, you need to open the PPT directly, not in the here.
Yes. I downloaded it.
Download it and open it directly. So it will be in the presenter mode. Pixels. That waste time. So very 10 minutes work.
Don't worry, you can extend 10 years. Don't worry.
It should be in the presenter mode.
We have this one.
Connect
Bharat,
connect the HDM. It will go to the presenter view.
This is in presentation mode.
No. Presenter view will give notes to it.
No.
Next slides and all. When you connect it, it will get projected.
USB ಇದ್ದಿದ್ದರೆ slide changer.
I can do from here, that's not issue.
No, they will take your this one photo. Yeah. So very good morning to Unanda. So welcome to the second day of this program. Today we have the renowned speaker Dr. Anjani Priyadarshini. Dr. Anjani Priya, a quantum physicist with a PhD from Indian Institute of Science, former national lead for quantum technologies, AWS India. Dr. Priya's journey began as a software engineer at Infosys before earning her PhD from the Indian Institute of Science. As a former technical lead at Soham Innovation Lab, she led the development of an indigenous hearing screening device for newborns. The team earned the national award. Later, she worked as a computation and algorithmic specialist in quantum and Robert Bosch. She predominantly works in computational mathematics and quantum algorithms. In the field of quantum, her expertise was primarily focused on algorithmic specialization across various domains, encompassing the automotive industry, aerospace, robotics, drones, computational fluid dynamics, finance, supply chain management, factory optimization, agriculture, material science, drug discovery, and many others. With this brief introduction about Madam, on behalf of KST and all of you, hearty welcome you, Madam, for taking this session. So please give her a big round of applause. Please, madam.
Good morning. Where I need to start, like how many of you are familiar with the fundamentals? What is quantum computing? What is the difference to quantum computing? Okay, let's start with some questions then. I'll understand the pitching, then I'll understand where to start. We have a laptop. So there is I want to do some compute. So which are the scenarios I want to use an institute server to use my compute? I have a laptop, I'm doing some MATLAB or Mathematica or some Python programming, any computation program for any discipline. I have some 100 lines of code. So which are the places I will decide my laptop is not working, so I need an extra CPU or GPU. When I will decide I need a server, when I'll decide I need a supercomputer, maybe I need to go for the cloud, or I need an extra resources. So what can be indication points for me to switch over to multiple hardwares?
Servers will document is not storing.
No, question is simple. I have 100 lines of code.
Processing slow.
Processing, so that means the time, how much time actually is running. Time complexity.
Document, yeah.
Time complexity. What else? Again, large simulations instance like time complexity, the time actually, it is taking more time than expected. Anything else? Huge data. Yes. Suppose I'll give a scenario, I have 100 lines of code, maybe I have a programmer algorithm, I'm doing some computation. it is running impractical timelines on my system. Suppose take an example, what I mean by impractical timelines. Every use case has their own benchmarking. Suppose if we are doing a stock market analysis or something, so I have suppose 1 lakh rupee in my hand. So I am using some asset allocation algorithm. It has to tell me, the algorithm has to give me, so what are the assets I need to go for it, like this, a stock 1, stock 2, mutual fund 1, mutual funds 2, and it will give me the different denominations for this 1 lakh. So if that algorithm is running for 2 hours or 4 hours, so what are the options I can look for? Suppose the algorithm is running for 2 hours or 4 hours, that means suppose at 9:15 the stock market will be get open. So it will take the input as the existing stock. The stock 1, what is the pricing, stock 2, it will take the input this one. I have an algorithm. If the algorithm is running at 2 hours or 4 hours, my input data still relevant to me? So for financial use cases, especially for stock market, the time complexity has to be done in the fraction of seconds and minutes. Suppose if it is a traffic optimization problem, it will give you few more minutes for us to not to solve the congestion. Suppose if you are doing some agriculture problems, it will give you a few hours for you. So if you are doing some drug discovery algorithm something, it will give you a few more months for you. So every use cases, every computational problem has their own practical timelines. So whenever I am doing something on my laptop, the next I will go to the server, or I will use a CPU, I will use a GPU, or I will use the HPC machines, or I will use for supercomputers, or I go for the cloud for like infinite amount of resources. All these things I will take for 2 reasons. One is that the time complexity, how much time my algorithm is running, and accuracy, how accurate my algorithm is it. So tell me the fundamentals, let's start with the fundamentals. So what is the difference to classical and quantum computers? Okay, let me ask you one more question before. Go back to the same question. I have 100 lines of code. I need to complete the program in 10 minutes. Instead of that, my program is running for 3 months. So there are algorithms which run for years and years. If you say take some drug discovery use cases, there are few simulations will run for 100 of years because of the complexity in the calculations. Suppose I have 100 lines of code, I am running it, it is taking on my institute server like 3 months. So what are the options? I will give it a try to reduce the time complexity to impractical timelines. What are the options I look for? Fast computing, that means instead of different CPU, different GPU, or I do for HPCs, I do for advanced hardwares. What else?
Memory.
Distributed computing, that means a parallel programming. So like I have 100 lines of code, I will make it independent chunks. So I am just using a parallel programming, the independent chunks we are processing to different CPUs and we are doing it. What else? Parallel programming is one, using advanced hardware is second one. What else? Supercomputer, same thing. Either we do the HPC or we do the parallel programming or we do the advanced hardware. What else you can do at the program level? Optimization. What you are going to optimize it? The whole idea is to reduce the time complexity. How do you optimize it? What you are going to optimize it? So one thing is that you have algorithm 1, algorithm 2, algorithm 3. So algorithmic optimization, finding a right algorithm such that suppose I am doing as algorithm 1, it give me 3 hours, algorithm 2 will be 10 hours. So I will check multiple algorithms and I will decide which algorithm will give me the best complexity. What else? Algorithm complexity, parallel programming, advanced hardware is done. What else? What else we can give a try? What? The cloud is same thing, right? Exploring a multiple hardware capacities. Reduction of a problem. So instead of solving a bigger problem, we are solving a small problem. So suppose someone asked me across the globe, what is the travel modality if to visit each and every country, what is the travel modality, or make an algorithm or a framework to understand how can I visit each and every country in the world. Instead of traveling across the world, I will take a continent. In the continent, I try to visit all the countries. I will try what is the visa, what is the mode of transport, distance, travel. So I'm solving a small problem. We are projecting back to the larger dimensions. So after doing all these things, when we are unable to get in the practical timelines, then we go for alternative computing. Let me start with addressing a few misconceptions about quantum computing. Quantum computer is not a faster classical computer. So I have a program. If it is running on a classical computer 100 of years, I just can't upload it on a quantum computer and expecting it is going to do shorter time. It's not a faster classical computer. And second thing, if you compare the clock cycles, quantum computers are much, much slower than a classical one inherently. But still, why we need it? It has a richer class of algorithms which works certain algorithms, certain domains, certain problem statement better than the classical computers. So when you take suppose I have 3 chairs here, in how many ways I can organize these chairs? 3 factorial. So as the problem size grows, suppose I have 10 chairs, 10 factorial. If I have 100 chairs, 100 factorial. Whenever you are solving a bigger problem, when the problem size grows, if you do a classically, that will take exponential time to solve it. But when you compare it at the smaller scale, the classical computers works better than the quantum computers. The quantum computers can give you comparatively a benefit only when you have the larger problem size. So what exactly quantum is going to do? Now we'll go back to the fundamentals before I'm explaining what are the things. So what is the difference to classical and quantum computers? Fundamentally. How I can distinguish the classical and quantum fundamentally? Exactly. So how the information is stored, how the information is processed. Tell me how the classical computer is storing the data? So I'll open this laptop. So inside I can see only the motherboard. So what does it mean a 0, 1 to that laptop? Voltage fluctuations. So whenever I type my name Anjani, it converts to ASCII. Some 0, 1, 0001, it will give to ASCII. So how the quantum computer represent that one is a 0, 1 in terms of the voltage fluctuations at the microcontroller level or microelectronics level. So if it has a 0 voltage, it is a 0. When it has a 5 voltage or high voltage, that is a 1. So what is the quantum computing analogy for us? So how many ways we are building a quantum computer? So people are using multiple technologies to build the quantum computers. Some people will use superconducting technology, some people will use ion trap technology, photonics, topological, spintronics, photonics. So the fundamental difference is that what we are representing a bit. The way we have a microcontrollers taking a 0 voltage and 5 voltage, we need some analogy in the quantum computers to store the information and to process the information. Suppose if you are taking a superconducting technology, so we will create a small tiny electrical circuit. There is an electrical current will flow without a resistance. So this tiny electrical circuit will give the energy levels for me. So these energy levels we are calling a qubit. So the way we have a classical bit 0, 1, similarly we have a qubit a 0, 1, 1, 0. So here the energy levels of the tiny electrical circuits we are calling a qubit. Suppose if it is a photonics one, so the polarization, the vertical polarization, horizontal polarization, we are calling it a qubit. If it is a trapped ion, so by using electromagnetic lights, we are trapping a charged atom. So this single atom is completely controlled by lasers. It will exhibit at different energy levels. These energy levels again we are calling a qubit. If it is an electronic based one, so like photonics, there is fundamental electrons. we are calling a up spin is a qubit, a down spin is a one more qubit. So similarly, there is a topological, NV diamond, spin quantum. So we need to identify what exactly we are calling a qubit. Is a qubit. Like if you have a up spin, we can call it a 1 qubit. The down spin is a 1, it's a 0, 1. So in between all the tilts will come in between 0, 1 superposed things. So I'll give you a scenario. So there are few thousand acres of lands are there, like it can be berry land, it can be cranberry or blueberry or some fruits. Okay. So let's start with the understanding where the quantum computer can give the benefit to you. So it's agriculture use case. I have a few thousand acres of land, so berry land. So there are two ways. First thing, why I need a computer at agriculture? Why I need to use a computation at agriculture? What are the scenarios I'll encounter there? Weather conditions, okay, fair enough. Anything else? Exactly, the disease analysis and crop estimation. As there is a few thousands of acres of land, there are two things happens. One is that it is there is no uniformity where the fruits are getting ripe. And second thing, if this some trees will get infected, if we don't go and address it, it will go and spread across. So human is not possible because we have few thousand acres of land and sending a humans and checking like the trees and fruits and daily basis is not possible. It's again the investment. So what generally do where the people will do in the the business side of agriculture, they use drones. So there are drones, they will take the pictures. So back end you have some machine learning or computer vision image processing, whatever you call it, you run algorithms. The input of that algorithm is all these images coming from this drone. It does some image processing. It will give you the coordinates. Those coordinates will give you what are the trees got infected, what are the trees they have the ripe fruits in that, so that you can pass the coordinates to the resource people so they can go and pluck it and take the next steps. Suppose the drones are actually cheaper comparatively the market. What is the cost of the camera? So if you to identify the right image, you need a good quality of the picture, right? So the moment if you need a good quality of the picture, you need to invest more on the good quality cameras. So where is the ROI? The entire the investment is going towards the cameras and this technology. So where is the ROI for doing the agriculture? So one point people will give a try, instead of using the high quality cameras, they can use a low quality and medium cameras. So the moment we use a low quality cameras, what happens? It will use a low quality picture. The whole heavy lifting is going to happen at the algorithm side. So the person who is sitting there, say the researcher or the programmer, the whole thing is that he need to extract the good quality picture from that faded images. Now coming back to the computer science people, so what kind of techniques I use it to extract that good quality picture from the faded images? Sir, I'm not from computer science, you need to be louder because I can't catch the words. Image analysis, okay, but in the underlying, what is the underlying process of image analysis? What I'm going to do that? Feature extraction is the first step where I start it. Okay, let me tell you, let me go back to the board. Any other guesses before I'm telling the answer? So there are 4 layers whenever you see the business to any research translation. The moment you say applied research or translation research, there are 4 layers. One is a business layer. The business layer will tell you, suppose agriculture is a business, so we are getting the crops, that is a completely business side. So next one is the application layer. What are the applications there in that business? And the down will get the technology layer. The technology layer can be AML or computer vision or HPC or a fundamental computing, what generally we do it at a mathematical level. So underline what we are going to solve is a mathematical layer. So if you see any kind of algorithm you are using in C, C++ or Java or maybe Python, try to open that library function and see it. So when you see the library function, it can be LBFG or it can be eigensol or anything in the MATLAB or Mathematica. If you try to open that library function and see what exactly that library function is doing for you, that will tell you exactly what kind of mathematical steps that library function is calling. The technology can be AML, you are calling some library function in the Python, but underlyingly you are doing some mathematics. My question is that whenever you want to do extraction of the real image, the quality image from the faded image, what underlying mathematics you are going to do it? Okay. In the SVM algorithm, what we are doing? That's the question. In the SVM algorithm, what I am doing it? Exactly. So in the algorithm, we are doing an SVM algorithm, a singular value decomposition or something we are doing it, or maybe you do like SVM algorithm, but for underline you are doing a matrix inverse. So whenever you are trying to extract the good quality image from the faded image, we are doing a matrix inverse. So how many of you done a benchmarking of any programming? Benchmarking profile. So what I mean by benchmarking profile, suppose you have some 100 lines of code or any algorithm or compute, there is a benchmarking profile available for all these programming languages. The benchmarking profile will give you, out of 100 lines of code, if it is taking 100 hours for me, each and every line of code, how many times it got interacted with the CPU or GPU, how many times it got interacted with the memory, how much time each and every line of code is spending that time. The moment you see, out of this entire program, only 1 or 2 lines will consume more than 90 to 95% of the time for you. Try to open that library function and check it. It can be a subroutine, it can be a function, it can be a module. Try to open that function and check it. It will take you to the library function. Predominantly, you will identify either you are solving a differential equation or you are solving a matrix inverse, or you are trying to solve singular values or eigenvalues and all those things. So whenever you have a numerical heavy lifting, that is we are calling a computational complexity. So if the algorithm is running for 2 days or 10 days or 10 years, underlyingly it is doing a numerical heavy lifting. That is why the algorithm is demanding that much impractical timelines for us. So why this numerical heavy lifting is causing that computational complexity for us? So going back to that matrix inverse problem. So I have a 2 by 2 matrix. So I want to do an inverse. How much time I require to solve it? A minute. If I have a 10 by 10, I will give to MATLAB. 100 by 100. Again, I will wait on the MATLAB or Mathematica or Python like a few minutes. 1000 by 1000, a million by million. So all these real-time use cases will ended up at least a minimum matrix. So I have a million by million matrix. So 1 million by 1 million. How much time the algorithm will take to do the inverse for this? That will run years and years of time. So what are the things are deciding how much time the algorithm has to take? I have a matrix, a huge matrix. What are the parameters decide how much time that inverse will take time? Size. What else? Sir, little louder please. No sir, look at the matrix side. I'm asking the matrix parameters. What are the matrix parameters will decide how much time the algorithm takes for me? Size of the matrix, agreed. What else? Ma'am? Exactly. The elements inside the matrix, sparsity. How many non-zero elements are there? The more dense the matrix, the algorithm will take more time to do the compute. That's why we do the preconditioning techniques. So whenever you do the singular value decomposition, eigenvalue decomposition, we do the preconditioning techniques to reduce that. That's actually reduction of a problem. The more you do the sparsity, we can eliminate that one. So what else? Rank of a matrix. That's why whenever see any algorithm, the assumption is that low rank matrices. So whenever the rank is high and the density is high, that means sparsity is very low, the size is high, that many arithmetic operations will be there. For each arithmetic operation, even take a nanosecond or microsecond, because of that much volume, the algorithm is taking hours and months and years of time for us. So whenever you do use a quantum computer to think of it, this problem can be solved by quantum computer, it is help you predominantly doing a numerical heavy lifting. So those subroutine, that function, you are doing an inverse. So those are the places you can introduce a quantum computer to offload this one to the quantum computer. In those cases, quantum computer will act like a CPU or GPU for you. So in the parallel programming, what we are doing, we are taking multiple CPUs or GPUs, we are offloading it. Similarly, quantum computer will be one of the CPU or GPU for you. So you need to identify what kind of mathematical heavy lifting can be done for that. The next one, hybrid computing. What I mean by hybrid computing, so same, take an example of the Berry project. So you have a image collection, extraction, feature extraction, do the machine learning thing, and then you have one place you hit at that A inverse problem because you are using a low quality cameras, you are forced to extract that real quality picture. So the entire thing, something you are doing on CPU and GPU. This is a classical compute. We are using a quantum computer as an extra CPU or GPU where it's like a Google map. You have a source, you have a destination. So wherever you have the congestion, we are taking an alternative way. So similarly, in that out of 100 lines of code, 1 or 2 lines of code will be a numerical heavy lifting for us. Those things we are offloading it to the quantum computer. That means entire computation you are doing in between a classical infrastructure and quantum infrastructure, it is shuffling back and forth with that. This is called hybrid computing. And the moment you want to use a quantum computer, you can't just copy paste and do it. There is no lift and shift. Quantum computers are completely works under different fundamentals. It is driven by quantum mechanical laws. And it has a different set of algorithms, different set of modalities. It requires different set of compute. If you have afternoon visit to the quantum computing unit, it looks like a big physics lab. So many wires and there, like refrigerators will be there. It won't look like this much compact and simple. So it has a different environment. So you need to rewrite the code and rewrite your problem statement in the way it understands it. And it has a different class of algorithms. So the way we have a Gaussian elimination, Newton-Raphson, we have a similarly a HHL algorithm to do that. And baseline, you have a CPU, you have a GPU, you have a HPC, you have a quantum computer. These are on the compute stack of it. Based on your problem statement, based on your requirement, the way you are choosing a HPC or CPU or GPU, you are choosing a quantum computer. And even the quantum computers comes in the full-fledged way, we are not going to replace this classical infrastructure. It acts like, most probably, it acts like an extra CPU or GPU for you. So where we are today? Any guesses what kind of industries are using it? Finance, yes. Pharma, healthcare. So wherever you see a computational bottleneck, I'll give you an example because the diverse people are there. Suppose if you take, anyhow I have a use cases, I'll go there. Whenever you see if your algorithm is running more than expected timelines, that's the first step for your check. Second thing, the algorithm has to fall into 3 general categories: the simulation, machine learning, or optimization. So these are the places quantum computer can give you a speed up, and there is no guarantee. Can give you speed up. You need to test it and identify it. Quantum is giving you speed up or not. But where to start it? If it is a simulation, it can be a physical simulation or a natural simulations or something with the nature. Like if you are simulating a molecules at the chemistry level or biology level or biochemistry level. So something you are doing a simulations. And if you have any optimization problem and machine learning problems, you can give a try testing on the quantum computer and identifying quantum computer's cup of tea for that use case or not. But as we don't have a full-fledged universal quantum computers are ready right now, you will encounter two ways. One is that quantum can give you an answers, but it's not superior than a classical ones. It happens because it's not ready. So from that output, what you are understanding it, I can solve you, but I'm not enough to solve you. So once the quantum computer, this error mitigations and everything ready and full-fledged configurations is there, it can solve you superior to the classical computer, but right now it's not ready. Some problem statement, it give you a time complexity benefit for you, but it has to be on the small scale because what are the computers available on the small scale for us. So predominantly what's happening in the quantum, who are the people are using it? The research people. The researchers at the academia, the researchers at the industries, national labs, or the people from the industry research. These are the people predominantly using quantum computers. To build quantum computer itself is a one R&D. People are using multiple technologies to build the quantum computer. Identifying the right stack for that. What are the different SDKs to do it? Identifying the right applications, identifying the algorithms, and identifying the solution for those use cases. Those are multiple ways. Before I go to these industrial use cases, just to give a completeness, I'll just cover a few fundamentals. I don't have slides. So if you are coming from the physics background or science background, the best way, as so many people are interested to float a course there, the best way to start it, how you are introducing quantum computing. So if you are coming from the physics, you will start with the Schrodinger equation, superposition, entanglement, and all those things. Suppose if you are coming from the computer science background, the better you start from the complexity. So what is the polynomial class? What is the NP hard? What is the NP complete? What is the big O notation? Where is the complexity coming? So from there you are going to quantum computer. The quantum computers works on the logarithmic complexity. So the way you are introducing from the complexity point of view. Suppose if you are coming from information theory background or ECA electronics background, you are starting with the Shannon's entropy. So how the information is stored, how the information is processed. So as it is an interdisciplinary subject and no one owned it, it's not about the physics, it's not about the computer science people, it's an interdisciplinary subject. It is like a catalyst. The way I explained you, the way you are using CPU, GPU or HPC, you are using quantum computer, it's like a catalyst or an accelerator to speed up the process. So the best way you can introduce a quantum as mathematically. So I have a 0, 1, a classical. So this way I have a 1, 0, 0, 1. These are just the column vectors. So classically I am representing a classical bit as a discrete variable 0, 1. When you go quantum, sir, any question? Sir? Mic is not working. Oh, sorry. I'm audible, sir? Sir, now? I'm audible? Yeah. So this is a basis state, or you can call a basis vector or coordinate vector, whatever. The way we introduce a differentiation and integration, the differentiation is that the summation, it's a discrete. So when you go for integration, it has an infinite space, but it's continuous. The fundamental difference to classical compute and the quantum compute is a discrete and continuous. Suppose I'm taking staircases, if I'm at the ground floor. If someone asked me to quantify my position, I can say I'm at the ground floor. The moment I reach the first floor, I can say I'm at the first floor. So how can I quantify a state in between? Number of steps. So if I want to quantify it much better, mathematically if I want to quantify it, so I have only two states, a ground floor or first floor. So what I can say, either a 30% to ground floor or a 70% to first floor, or I can say a probability 0.3 and 0.7, or I can say amplitude, or I can say the in terms of norms. So whatever you say, the state in between the first floor and ground floor, I am able to quantify into the superpose of two states. This is what we are getting a superposition concept. So the first fundamental rule where we are getting this time complexity compared to the classical one, superposition, entanglement, inference, these steps. So if you want to, if someone wants to float a course, after this I can share that contact details. We can help you what are the topics you need to cover, what are the learning paths you can do it. But better start at the mathematical way, because this interdisciplinary this subject. The moment you start the Schrodinger equations or Shannon entropy, the people are coming from non-discipline background, they will get scared and they will leave the class in 2 days. So better start at the mathematical way. This is actually a +1 +2 mathematics. So whenever the moment I say it is a combination, it will be there somewhere here. It can come, it can be 3, 4, it can be 5, 6, the 50. So any data point is a simple intermediate the mathematics. So any data points, any superposition state, you are going to split in terms of two combinations. So it's a like a 0 or 1. In the block sphere, you can have a 0, you can have a 1. Is everything will lie inside the sphere or outside the sphere on the sphere. And next one is entanglement. I'll just give you a glimpse of entanglement. So if I have two elements, what are the combinations I can express? I have two coins. I have 2 coins. In the 2 coins, I have a head and tail. What are the combinations I can express if I am tapping the coins? So 0, 0, 0, 1, 1, 0, 1, 1. Suppose I have xx plus xy. I can simplify it further, right? X into x plus y. Suppose I have a xx plus yy. So there is nothing to simplify it further. So similarly, when you are doing with qubits 1, so you will encounter the similar state when you have a, so there are multiple ways, 0, 0, 1, 1 or 0, 1, 1, 0, where you are unable to separate it. These are entangled, these are tangled each other. So these are like more go on the security side. I'm not going to much details. Suppose there is some soldiers carrying some security key. So they split the code. They split the code, they have the 2 different balls or security, they are carrying it. Suppose one soldier caught by an enemy, if they want to reveal that code or they want to tamper it, the moment other thing will get destroyed. Suppose you have a 2 red color balls where carrying each other, the guy has taken that one out. Suppose I got caught, if someone took the ball and they want to paint it or break it or whatever, the same thing happened to that ball. So you can't retrieve that information together. So the mostly this entanglement concepts will use for the security purpose. The entanglement, superposition and inferences, interference, these 3 are the concepts where we are getting the speed up. So what are the classical gates? XOR, NOR, NAND. Which gate is this? NOT gate. Is this correct? The line is there, I didn't remember. So similarly, we have one is the classical bits versus quantum bits. One is the discrete, one is the continuous. You can explain that one from the block sphere point of view or anything, better you can explain with the vectors. So simply a qubit is a vector, a 2 by 1 column vector. Because it's a vector space, we have a infinite elements available inside the coordinate space for us. The next one is gates. So what can be the gate here? Because I have a 1, 0, 0, 1. It is a 2-bit system, 2-state system. So I can't do in one line. So this is the 2-qubit system. I have a 1, 0. So this is a control. This is a not. Whenever I have a control, that is like a switch. It's like a switch. Whenever the control is 1, it will act. So it will be 1. It is acts like a NOT gate. It will switch over. So if I have a 0, 1, it will be 0, 1. So what is that gates? If I have a qubit is a column vector, what is that gate? Okay, let me ask you precisely. I have here 1, I'll get a 0. Okay, so there is some operation happening here. It can be a force. I have a initial state, I'm pushing it, it can be a translation force, right? It can be a pressure. So all these things are operators, right? Force and momentum and pressure, all these things are operators. So similarly, I have a electronic circuit which is doing 1 to 0. So in quantum, I have a 1, 0, it do some operations, it come to 0, 1, or it go to 2, 3, whatever. I have an input, I have an output. So what is this? What can be that if I have a column vectors? Matrix. So a gate or operator, whatever you call it, it is simply a matrix. It's simply a matrix. This is your input. This is an output. So an operator or a gate, whatever you call it, that is a simple matrix vector multiplication. So how much heavy circuit you have it, every line it is doing only a matrix vector multiplication for you. So at the end I will get again a vector, what's called a measurement. I have a coin in hand, it can be head or tail. It can be head or tail. It's a head, this is a tail. So it's a classical or quantum? Yes. Classical. So I'll tap the coin. So it rotate it. In the air is a classical or quantum? Because any point of time I can say this position as a combination of multiple positions, that's why it's quantum. The moment I tap it, it's a classical. So that tapping is a measurement. So you have an input, you have an output, you have input, you have some output. So in between you are doing multiple operations, anything. These are a simple matrix multiplication. Again and again we are doing a matrix multiplication. So the tapping, the measurement. So whenever you do a measurement, the system automatically collapses to the quantum state to classical state. That means you will get, suppose this is a 3, 4. So in the measurement, what you will get? An amplitude or probability. So in which state, at how much amplitude, how much probability is landing it. So you will get those numbers. So any questions for these fundamentals? I'll go for the industrial use cases. No ma'am, it's not. We don't have analogy. Only not gate we have it. Suppose similarly like there is an algorithms can replace a Gaussian elimination or something. There is no lift and shift. We don't have a one-on-one matching. As it is a quantum mechanical nature, the system should allow you. The wherever the machine learning problems, optimization problem can help, but there is no one-on-one matching. It's not.
Means we have to develop a separate quantum machine.
Yes, that's what. The entire system will be different. The way information is storing, information is processing is different. The gate set is different. The algorithms are different, the stack is different, it's completely different. So that's why when you're solving A inverse problem, take an example. If you want to do classically, we do Gaussian elimination method or Newton-Raphson method. We do HHL algorithm. You need to reformulate the problem such that it understands.
But you told, ma'am, like when it is in superposition, so the quantum computing it will act. So when we tap it, it is act like a classical computer, correct?
Yes, ma'am. Tap it in
So
sense.
part of the information I am giving to the quantum computer to solve it.
Yes.
I am taking a big question and splitting it into a small question. I am solving the problem. So where the quantum computing it will come in between, like a classical, between classical.
It's like a machine learning problem. In the machine learning problems, you will start with the initial variables, right? So I have your x0, x1, x2, x3 something. Then you try to identify the weights and bias. Okay, you have some algorithm, set of algorithm which and give a first level of weights. So again, you will go back and fine tune your initial parameters and redo it, right? So if you see that initial parameters are classical, this algorithm is quantum, you are getting an output. You are getting an output. Based on the output, you are going back and changing it. So in the same image processing problem, so you are passing your images to there, or you have 100 lines of code. In between, you are doing A inverse. So only that part you are reframing it and giving to the quantum computer. So when you solve A inverse problem, what you will get? X. So x equal to A inverse B, you will get an X vector. So you will get a quantum mechanical X vector there. You will convert to the classical mechanical, you will reuse it. You will reuse it. But whenever using quantum systems, you need to reformulate the problem, and the entire the information will be in the vector language, not in the discrete way. That means instead of doing it n dimensional, you are doing a Hilbert space of 2 power n dimensionals. Sir, any questions at the fundamentals? Yes, ma'am. I'll give you an example. Suppose someone is coming a biochemistry background or something. I have a use case there, I'll tell you. They do MD simulations. They do MD simulation. So they generally do MD simulation on the MATLAB. So whenever you do the MD simulation, you do with multiple amino acids, how many protein foldings happens and all these things. It will be like a very computationally heavy problem because it's quantum mechanical in nature. So that they will offload to quantum, but I understand this classical and quantum, this interaction is only possibility. You are not offloading everything to quantum. Even the quantum computer universally, quantum computer is ready, it's not going to disrupt the classical structure. The way you are translating CPU to GPU is a similar language, that's why it's a free flow. In quantum, you need to translate it in the quantum, and you need to translate the solution and feedback it. It won't be a problem. So if there is no questions, I'll go to the industrial use cases. Look at the picture. This is the logistics and supply chain. There is a cargo container. It is starting from a source. It has few millions of goods, and it has a 200 destination points. Simple. There is a source container starting from one place. It has to deliver the goods at 200 places. So why I need a computer to solve it? What I'm going to optimize it? Little more precise. Exactly, the traveling salesman problem. If I have a 200 paths are there, there is a 200 factorial ways I can identify it, what comes first, what comes later. So 200 combinations, 200 factorial ways. What else? So traveling salesman's problem, identify the shortest route, which is the best shortest route for that cargo container to deliver all the goods. What else? Look at the picture, you'll get a clue. You're nearby. What is the problem in the loading? Exactly. In the loading, in which order we are organizing it. Suppose in the destination one, the good has, the package has trapped somewhere in between. I need to offload all the container ships. If I have a million goods, million factorial ways it is there. So in which order we are stacking it. So, whenever you do this kind of a heavy lifting problems, these are the places we are using quantum computer to solve that. So, agriculture, which I explained you earlier. So, one is that when you are using a drones kind of thing, the machine learning problem, and the fertilizers. So, whenever you are creating a fertilizers, you need to simulate ammonia molecules. So, simulating an ammonia molecule is a very high complex problems. There you can use quantum computers to solve it. So, I'll just give a little dive deep into this. Is anyone from biochemistry, microbiology here? It's completely irrelevant. Just let's skip it. In electrical sector, so grid optimization and power dispatch problems. How many of you are aware of the power dispatch problem? So, grid optimization problem is that you have a how much balance, how much supply is there, how much demand is there. So, if you have a generator, you need to generate power. So, how much is that the supply is there, how much demand is there. This is the power flow equations problem. You need to solve a power flow equations. There it is a linearized iterative model, generally we do it. It can be Newton-Raphson or Gaussian elimination. So, these are very complex problems where the classical computers, even supercomputers will take long time to solve it. Similarly, power dispatch problem. We have a centralized power station in the country. So, it has to identify how much power has to be dispatched to southern part of the country, north part of the country, east and west. So, whenever you are doing this one, you are predominantly solving like this power flow equation. This is the constraint optimization problem. Right now in the Kstacademy machines itself, it is running for 5 minutes. But as I told you earlier, every use case has its own practical timelines. The power dispatch problem, the 5 minutes is not practical. It has to be completed in 1.5 minutes. So, it can be a power dispatch problem, grid optimization problem, agriculture problem, or a molecular docking or protein folding. All these problems has the different time scales on the classical computers. We are going to check it if it is falling into 3 general categories: optimization, machine learning, or simulations. We are giving a try. As I am telling you, there is no prescription to say which technology can build a universal quantum computer. Superconducting, photonics, ion trap, there is no prescription to which technology can build a quantum computer. Again, there is no prescription to say you have multiple quantum computers available which can give a benefit to which domain and which industry. We need to test it and identify it and check the benchmarking, and coming to a conclusion, this technology, this quantum computer is giving a speed up to my problem. And again, suppose take an example, if you are in the finance domain, if you are doing a portfolio optimization. So, you are saying so and so computer is giving a speed up. But in the same finance thing, if you have an asset allocation problem, there is no guarantee to say that this asset allocation problem can be get a speed up on the same quantum computer. So, we are still in the very early days of R&D and identifying it, which technology is giving a speed up to which domain. The one last slide, automotive sector. This one actually I have a very good material, you can Google it out. If you are interested, you can drop me a message in LinkedIn, I will share that thing. This is from AWS BMW challenge. So, the problem statement will help you if someone, as ma'am asked her, right, how this classical and quantum intersection is happening, is it can't be hampered, that complexity and all those things, you will get an idea. Those are 4 different use cases. By reading this document, what you will get it, how to formulate a problem first, how to formulate a business problem. From the business problem, how to come to a conclusion. This is mathematically like a computationally complex problem. Why it is taking much time in the classical computer, how a quantum can help it. It will give you a little thought process for you if you read the docs. So, this is like from automotive sector. So, one is a pre-production vehicles, material deformation, sensor placement, and the quality assessment. How many of you are aware of the crash test? Crash test. In YouTube, you will see, right, there is a car, there is a robot will set it, it will go with the high speed and hit the wall. Yeah. So maybe like lot many people know the crash test, right? So whenever they are dispatching a vehicle to the ground, so they do multiple tests. There are approximately 160 to 170 tests are there. This one of them is crash test. The crash test will tell you if the vehicle hit any object, it can be a wall or other vehicle, what is the impact on the car, what is the impact on the driver. So they do this approximately 170 tests to certify a car before they are getting into the market. In which order I need to keep this? Out of 170. Suppose I keep something in the wrong order, so I need more cars to do the test. Suppose after the car test, the car is nowhere useful for to do some test. So similarly, in different tests, the brakes are like this air balloons or maybe other metal body will get be like damaged. So in which order you need to keep this test? One thing. And second thing, in the material deformation problem, in the very old days, to build aircraft or a car, first thing you need to identify the right metal for that. Which metal I need to use it? It can be a rocket, it can be like any vehicle. Which metal we need to use it? Because if it is going on extreme temperatures, it shouldn't get melted, it shouldn't get deformed, the shape shouldn't change it, you shouldn't get the holes or cracks. So whenever you go for very extreme temperature of the like a cold or hot, like whatever, and the different speeds, you shouldn't get deformed it. So whenever you do take a different two metals, in old days we'll do multiple combinations, we'll melt it, there is a big, the car or brake or whatever the mold will be there, we'll create a mold, we'll do a physical testing. Nowadays we do a distal forming. So distal forming is like algorithms kind of thing. The people who know CFD simulations and all, you know it. So you will give an input, the metal 1, metal 2, what is the stress, what is the strain, what is the viscosity, what is the density, what is the boiling point, we will give all the parameters. There an algorithm will run and identify the right alloy of this mixture. In this right alloy of the mixture, when you are solving it, you will end up solving a Navier-Stokes equations. That means, like if I say very very less technical, you'll end up solving a higher order partial differential equations. So these solving higher order partial differential equation with that biggest size, the minimum matrix where you will hit it is million by million. So when you are trying to higher order partial differential equations, it will take a very large amount of time to solve it. So what I will do if taking large amount of time, I reduce the problem. Instead of solving higher order partial differential equation, I will try to reduce it to low order partial differential equations. Again, I don't have an algorithm which can solve it in the practical timelines. If the algorithm is running for 10 years, 20 years, it's not in use, right? So I'll reduce further. Again, I don't have an algorithm, I'll accept alpha error. I'll change it to the ordinary differential equations. Even though I don't have an algorithm to solve it in time. I'll further reduce to linear system of equation, that is Ax equal to b. So I have an equation which can need to solve it. I'll end up here. Okay. Then I'm reducing this one to a lower order partial differential equations. So I'll just go by something. Again, I don't have an algorithm to solve it. I'm accepting alpha error here. Okay, the solution plus alpha error. So I'm reducing the problem. Again, I'll go for beta error. So what I'm doing it, I'll do it for a differential equations. Again, I further reduce this one to an x equal to b. In the Navier-Stokes equations or lattice equations, whatever we do it, I'm reducing to a small system of equations which is x equal to b. So what I need to calculate here, suppose x equal to a inverse b. This is as simple as the matrix inverse equation. Again, the moment I'll end these equations, I'll end up with a million by million variable. Again, the rank of a matrix, size of the matrix, sparsity, everything will decide how much time that matrix will take time to get the inverse out. So these are the equations running on the supercomputer years and years. So those are the places we upload only this. Ma'am, this is the answer for you. This is a material deformation problem. The entire thing we are doing classically, only one place you have the bottleneck, the computational complexity, only that single line, a piece of code we are offloading to quantum computer. So, there I am calculating x, a vector x, but the x vector I am deriving from the quantum system, I am feeding it back to the classical systems. So, similarly sensor placement problems, this is a combinational spatial optimization problem. Which are the places I need to keep the sensor to get the 360 degrees coverage? And it can be, if the quality assessment problem, it is the machine learning problems. So, these are the different areas you will get a different set of computational complexity. So, you are going to identify either CPU are going to solve it, or GPU is going to solve it, or quantum computer is going to solve it. And to conclude it, quantum computer is not something, even it comes, it is not going to disrupt the classical systems, it is going to act an extra CPU or GPU to you. It is sitting next to the same computational stack where you have a CPU, GPU, HPC, next is quantum computer. Again, there is no heavy lifting. You need to rewrite the programming to the language what quantum can understand. It's a simple basic Python language itself, and it predominantly does a numerical heavy lifting for you. So, I'll conclude here, I'll take some questions.
Which is working on classical computer. We wanted to shift it on to quantum computer. What are the, how commercially viable, regardless of the accuracy and other facts or benefits of quantum computer?
It's a little diplomatic answer, sir. As I told you, right, whenever you use quantum computer, it can be R&D level or industry level. It will be two ways. One is that it solve it, but it's not superior to the classical. Sometimes for small module, it will give a superiority. It's superiority in terms accuracy or time complexity. I know a lot many healthcare or pharmaceutical companies are got that superiority, like better complexity, but I can use the word better time complexity. So, there are so many published papers saying that when you do the MD simulations on the supercomputers compared to they are using variational quantum eigensolver and VQE algorithms and all those things on the quantum computer, it gives a superior time complexity for them. Commercially viable in sense, it's not completely a production level use case, but a small modules you can use it in the quantum, but not entire use cases you are not doing in the, that's not, that much commercial grade is not there.
Okay, so for example, some companies, they don't have supercomputer and wants to take benefit of that. So only the simulation is the solution, or you can have any other way?
Sir, one thing is that you are going to do only compute, nothing more than that in the quantum. You are going to do compute. Whenever you are using HPC or like other quantum computers, you are simulating this one on the quantum computer, exactly you are doing a simulation. But commercially, like a lot many industries are using it. There are plenty of industries from automotive they are using it, and like healthcare, pharmaceutical, energy sector and finance, a lot many people are using it. But at what grade depend on the problem statement. Some people are using to solve a small set of problem, but it is giving an accelerator. But some people are identifying it, can I adopt it, can I create a workforce inside, is my use cases is working on quantum, they are keeping an evidence, based on that they are actually working further. Ma'am.
Thank you.
Ma'am, validation is, see how do you validate a classical first? So, suppose you are doing some MD simulation, you have a traditional algorithm, take an example, you have a Gaussian elimination algorithm, you keep a benchmarking, you do Newton-Raphson as a benchmarking, and you will do a new algorithm to compare it. Similarly, here the one thing way you can compare the classical thing itself in terms of time complexity and accuracy and the resource cost. The trade-off is different, ma'am. Whenever you do quantum comes is the more costly than the classical. But whenever you run an algorithm, one thing is that how much time the algorithm is taking, how much accurate the results, how many resources we are blocking. Suppose supercomputers, if you are running for 10 years, what is the cost? What is the cost you are maintaining to maintain the resources for 10 years? How many human resources you are paying it? How much cost associated? All together is a trade-off for you for the quantum. But at the algorithmic level, you can compare it as of now with the same. The Gaussian, I got the x in the Gaussian elimination. I got the similar x there. No, ma'am, there is no lift and shift. The algorithm won't work. So you need to find the counterpart for the quantum. Suppose if you have a like a matrix in a Gaussian Newton interruption, there is a HHL algorithm. So there is they need to identify the counterpart there. The same algorithm won't work on the quantum because the information is processing in that algorithm itself is a classical, right? It won't understand. Any other question? Yes, sir. Yes, sir. Actually,
Every use case does it make sense to have a single supercomputer, or use case specific is a better choice?
sir, please come again. Well, you asked us something universal quantum computer.
I mean, does it really make sense to have a universal super quantum computer for every possible use cases, or is it better to have a use case specific quantum computer so that it is more meaningful?
Sir, it's not like that, sir. Actually, quantum computer is simple. One single quantum computer. We are identifying it's working for us or not. You can't change the different, but there are different technologies. Some people use superconducting, photonics, ion trap, spintronics, and all those things. But we don't know, right, which technology can build a universal quantum computer. Even it's ready, we don't know which technology will get benefited.
Even if it is possible, does it really make sense to have it one?
Yes, sir. It makes sense because these drug discovery use cases will run hundreds of years, literally hundreds of years, few hundreds of years. But until unless the systems are ready, we don't know it will get benefited or not. So we need to make the system first. But to identify which use cases, which domain, we don't know the mapping right now until unless we make it.
Okay,
If it is ready, 4 or 5 is ready, I can know this is working for me, this is working for me. There is a different scalable level. Suppose if you say the superconducting systems, what is there in the right now availability, with a few thousands of qubits. But if you go for the photonics one or anything, it has a few number like 8 qubits or 10 qubits or something. This is a different scale. But we don't know when this will get changed. This is completely R&D process.
okay, thank you.
So depend on use cases. Suppose if you are taking a tiny problem, 8 qubits will be sufficient for you. If you go for the commercial problem, sometimes 25 qubits or 36 qubits will be sufficient. No, sir, not it. No, sir, there is a difference to simulator and logical qubit. In between, there is a quantum computer. The simulator is not a quantum. The simulator is the one we are using a regular HPC machine or classical computers with heavy quantum heavy backend, we are using hardware. We are creating a simulator. It acts like a quantum. See, what is the difference to classical and quantum? Classical will give me order of n cube or n square n. So quantum will give me logarithmic n. So you are making a simulator such that it will act like a quantum, but it's not a quantum. After simulator, there is a quantum computer. So simulator backend is a classical. There is no quantum. So they hardcore it. See how they hardcore it. Like they will form a vectors. They will form a matrix. They will hardcode it. It completely hardcoded. I'll come back, sir. I don't know this. As far I know, they generally hardcode it such that they will transfer this information in the matrix format, vector format, and all those. They'll hardcode it. But I'll come to the precise answer. I'll come back to you. And in after the simulator, there is a quantum computers available before the logical qubit. So there are physical qubit. What is the NISQ? There is a noise intermediate scale available. After that logical qubit, one logical qubit required few thousands of physical qubits. So two ways, I understand your problem. See, first of all, simulators are available, but quantum computers are also available. You don't need to wait for the logical qubits. Physical qubits, whatever we have it in NISQ, that is also able to solve a small set of problems. This is where actually this BMW or other drug discovery use cases and all these things are saying. They used only physical qubit only to get the speed ups. Yes, agreed. Because it's R&D state. So noisy, all exist. Yes, that is also based on the framework it will change. Yes, there are complications is there. Agreed. After all these things also, there are proven results in the specific domain, specific problem statements. But to test it, you no need to wait for the logical qubits, because physical qubits will help you to this extent whatever we have it. The simulators are completely different. This acts like a quantum, but these are not quantum. I got it. I'll try to identify, sir. Thank you. Ma'am, please. Ma'am, I can give you a better answer. Actually, my supervisor, Professor Apurva, is a Richard Feynman student. Okay, so we are still in the second generation, but still we have few thousands of qubits. So now it is much faster than the classical. That's what we are able to see from the scientific evidences.
Okay. Because when we see that the books, because we refer the books and we see the classical computers as being a big, it is what is in a big room, IBM, that photos. The same thing is what we see in the quantum computers
Exactly,
with the
ma'am.
room. So what that evolution, when we take, it takes around 50, not 50, around 30, 35 years back, and we see the mobiles in our hands. No, that's an evolution of the technology. So the same evolution, what is the time span? Because we are very fast forward and we are into technological era, and students are very much into the coding, because these days students, those who are in the 1 to 7th standard, they know what is coding. So the evolution of artificial intelligence before the 10th standard, they are
Madam,
aware.
could you please stop the recording? As she took the right word, it will be a problem for me after this. Okay, ma'am. One thing is that coming back to the quantum computing and all those things, it won't take that much time as the traditional computers. That's for sure. Coming back to the coding, I want to because all your faculty. Don't create a workforce like the way we create it for softwares. So now you have seen left and right all the layoffs. Just because anything can be automated, ma'am, no recordings, right? Don't do me, please. So the moment these things will get automated, the layoffs will come. So don't just train the people only on how to program it, how to use quantum computer. So that means you are creating one more quantum software force. This will eventually get layoff layer. So the better way you can start, there is a reason for you to take a discipline, to become a faculty one discipline, or a student to take any discipline. It can be ECE or electronics or computer science, physics, chemistry. There is a ikigai of a student. There is a reason. Either they love the subject or they love the at the end point, which kind of job it will come from this. So leaving your core science and technology, engineering, going behind any technology is completely wrong way to nourish the next generations. HPC, when AMML started, everyone thought of it is only for computer science people. We thought it's for the data sciences and all those things. Now we realize AML is a tool. A biochemist can use it, a microbiologist can use it, a electrical person can use it. Quantum is a tool. The way you are using MATLAB, quantum is a tool. It works for electrical, it works for biochemistry, it works for microbiology, physics, chemistry, wherever. You need to identify the right thing where you can start your journey, train up yourself with the right certificates. So certificates won't help you, the right courses. Having a certificates in the resume is completely useless nowadays. No one is caring about it. So don't push the students behind certificates. Keep a proper course. Try to understand the course, try to understand the fundamentals strong. Later, after you completed the course, apply this one to your own science and technology. If you are coming from the information theory or computer science, AML or mechanical, I try to use this one to solve some problem statement in your own domain. Leaving it, just understanding a Python programming, how to access the IBM machines or AWS or Azure or Rigetti, IonQ. So if you are playing at application layer, that means a simple software programmers you are creating it. Try to identify how to use this quantum computer in your own science and technology. Second thing, hardware level thing is more important. So the India till now, what we had it on the application layer. What is lacking is manufacturing, fabrications and hardware layers. So identify if you have a student who want to interested in hardware parts, understanding how to make a control electronics, understanding how the fabrication labs works, and all those things. Anyhow, you have that visit in the afternoon, ask these questions and identify. Try to motivate the people not to be on the rentals of the systems. Use it, build the algorithms, build the softwares, build the SDKs, and do at the hardware and pulse control levels. But as there are 100 people, even 20 people got motivated to go the courses, again, you do multiple courses, certifications, don't create it. Take a problem statement. Take a right course for you, you train yourself, later identify the right course for students, but after this course, take a problem statement from your own domain. If you are struggling something, I can give my link, reach out to me in the LinkedIn. I will help you what kind of problem statement you can do it. In that domain, what kind of industries are investing on it. So try to solve the relevant problem statement where your strengths are lies. So you are good at your own field. Use a quantum as a catalyst. Identify the problem statement in your own field. Use a quantum or HPC AML as a hybrid model. Try to solve that problem. So whenever you train your students towards a problem statement, you will end up with the publications or patents. So one thing is that without a student, you can't enter into the community, because you need to, we used to work with a lot many faculties, the academia part, and there is non-academic things will be there, and assessment, exams, all these things. You are not the one sit down and do a research. That's not possible practically. It happens in IISc or TIFR or ICTS because there's a research bounded institute. They teach like only one course per year. But when you go to the regular academia, these are not something happens, because you need to balance your assessment, exams and non-academic things, all the things. Having an R&D project is without students is not possible. If you want to enter into the real-time community, you need to have a pool of resources. Predominantly your BTech students are master students. So when they are training on the quantum computing fundamentals of the beginning, the second year, third year, they will be ready. Take a real-time problem statement in your own domain. Don't try to solve a finance optimization problem and all those things. Take a problem statement in your own domain, try to solve it. So the moment you try to solve a real-time use case in your own domain, what happens? You'll end up with the publication or patent. It will help the student. Second thing, the more publication patents you have it in your own domain, it's easy for you to secure the funds from the government and industry. As you are trying to solve a real-time use cases, if you go get a chance to present this one to the industry people, the funds will come to you. So it is a systematic way. So fundamentally, work on your own domains. Use a quantum as a catalyst. And if you are struggling to identify the use cases, reach out to me. I'm the entire my quantum journey, what I did in the diversified the use cases in the industries. I can help you what kind of use cases are available, what kind of industries are working. You can check their websites, you can identify what is the roadmap of that, pick up some use cases. That's what best I can give an advice. Yeah.
We can discuss during tea. So anyway, it was very interesting and interactive session. Thank you very much, madam, for your excellent lecture. And I have one announcement. The next speaker is here already, and 10 minutes we have quick tea break. Before that, I have two announcements. First thing, we have one bus arrangement. Only it will occupy 45 people. Okay, and I am already sent a message in the group. So those who have vehicle, so please come with your own vehicle, or else you can follow us in the bus. So that's what my request. Otherwise, first batch will go, and you have to wait for another 1 hour to reach there. So that's what the scenario now. Second thing, So those who are coming, maybe 1 or 2 sessions, even maybe some emergency, that's okay. If you are coming half day, 1 day, it is really it is very problematic. You won't get any certificate. That's what it is, very strict measurement we are following it here. So I request all of you, please attend all the sessions. If you miss 1 or 2 session in emergency cases, that is okay. Otherwise, you won't get any certificate. If you request also, we will not give certificate to you. That's what the one concern. And I request 3 people have not received their receipt. Vindhya Hill, so please receipt from Bharat, and Dr. N. Nayanamurthy, and Akash Ashok Naik, please collect the receipt from Bharat during tea break. Please have a quick tea break, 10 minutes, and assemble back. So welcome back and good afternoon to all of you. So we have another the expert from QPI, Sri Sagar Dolin, presently working as technical manager, quantum software QPI. Sagar is a technical manager in the quantum software team at QPI, where he works at the intersection of quantum systems, software, quantum hardware, and enterprise business solutions. He plays a central role in building India's first next generation production ready quantum computing as a service stack, spanning software platforms, developer SDKs, APIs, simulations, and hardware integration. As a significant part of his work, focuses on applied optimization and quantum inspired computing. Sagar leads end-to-end implementation of optimization use cases as part of the QPI AI optimization product, translating real-world industrial problems into deployable solver pipelines. And Sagar brings a system-level perspective to quantum software development, emphasizing co-design across algorithm, software, infrastructure, and hardware capabilities. His contribution supports QPI broader mission of delivering practical, scalable quantum-inspired solutions that bridge cutting-edge research with real-world impact. With this brief introduction about Sagar sir, on behalf of KSTA and all of you, hearty welcome you sir for delivering this session. After this session, immediately please have a quick lunch and we can deliver later. Okay. And those who are sitting, backside, please come to the occupy the front seat. Please.
Hi everyone, I hope I'm audible. Okay, I am Sagar. I am a technical manager in the quantum software team at QPI AI, and I think my intro is already covered, but some of the technologies that I particularly work on is quantum computing and building quantum computing as a service software stack, and mainly on optimization use cases, right? So today I'll be covering more on quantum computing and some of the optimization applications, mainly focused on applications that we are working at QPI AI, and I'll also cover some of the algorithms and challenges that we face, and also when I say optimization applications, I'll be talking less about how we solve it, and I'll be talking more about what are the problems. So we'll basically see what problems today we are facing in the industry, so that you understand the complexity of these problems, why these problems are intractable, why these problems are called NP hard or NP complete, right? Okay, so just the introduction of QPI AI. So the vision of our company is to solve complex problems, and we solve these problems by intelligent modeling using intelligence compute, and the tools that we use for this are mainly AI and quantum computing. Now me as an engineer and as a researcher, my goal is to solve problems. If a problem takes quantum computing to solve a problem, we use that. If it takes some approximation algorithms to solve a problem, we do that. If it's solvable by simple linear regression or any other models, we do that, right? And some of the problems that we are facing today, these problems essentially require advanced compute, HPC compute, and quantum computing, right? The image that you see on the right, this is an image from our Bangalore facility. This is at QPI AI Carle Hub, and this is a picture of the quantum computer that we have. So what you see here on the right, this is called a cryogenic fridge. So this basically helps cool down the chip up to 7 millikelvin. I'll talk more about this in the later slides. All right. So what is it that we are trying to solve, and what's the hype about quantum computing? So to understand what's the hype about quantum computing, we need to understand what are the different problems that are not addressed in the market yet, and they serve great value. So if these problems are solved, then you basically have a sustainable civilization, right? So that's the ultimate goal of technology, to build a sustainable civilization, right? So these are some of the problems. Okay. So these are some of the problems that we are working on, and if you see this graph, so with the increasing modeling complexity, you require more and more compute resources, and the compute resources that we have today to solve problems at this scale. So this square box that you see, right? So this square box is basically the problems that we are targeting to solve, because rest of the problems you can solve with already available algorithms and compute resources. So what are these problems that we are targeting? Some of the problems are in drug discovery, material simulation. So material simulation meaning if you can define properties of a material, how do you simulate that? How do you make that material to get that desired property? For example, if you are designing a battery, you would want the battery to not heat up immediately and burst into fire, right? So you need to define certain properties, and from those properties you design a material. And this is not a simple task. It's a very complex task, and it requires a lot of compute, because what they essentially do is they try out different combinations of materials and simulate it, and it basically is almost as good as brute force technique. But of course, they do apply some smart heuristics, but again, a very complex problem to solve. Protein modeling, operations research, I think Dr. Anjani has already spoken about some of the problems in operations research. So operations research basically covers logistics, supply chain, production planning, manufacturing, automotive industry, all these industries, right? So our goal is to solve these problems, because these problems are still unsolved, untapped, and there is a huge market for these problems, and the ultimate goal is to have sustainable development. This is the profile of QPI. We are a team of 70+ strong engineering team. All our team members are either engineers, physicists, computer scientists. I'm sure it has gone more than 100+. I think I have not updated it from 70+ to 100+. So I'm sure there are more than 100 people working at QPI now. Headquartered in Bangalore, and these are some of the publishers where we were featured: Harvard Business Review, and some other publishers that you might have heard of. NASCOM has also published few articles on the use cases and on the technology that we are working on. All right, coming back to the quantum computer. This is the lab setup we have. The one on the left that you see, that is the cryogenic fridge. It cools down the chip up to 7 millikelvin. So if you want to know what is 7 millikelvin, it's almost close to absolute zero. And the lowest temperature that the universe can go is, I think, 3 Kelvin. So the lowest temperature of the universe at any point is at least 500 times than what this fridge can cool down to. So if you were to look at the universe with an infrared glass, you would see that this point in Bangalore is the coolest point in the universe, and some other places where the quantum computers are deployed, superconducting quantum computers. Photonics doesn't require to cool down the system, but superconducting chips do require to cool it down to 7 millikelvin. Now, why do we need that? I don't think I can answer it. Maybe chip designer or quantum hardware engineer can answer it, but I might give you some insights on how this chip exactly works, if there's time at the end. So today we are talking mainly about optimization. We have developed a product called QPI Opt. So this is an optimization product. So it's a platform, and we will talk more about this product. I want to focus more on the applications and use cases that you might be interested in. But I'll just have a brief overview of what this product actually is. So, any problem that you see today, be it a combinatorial optimization problem, for example, if you have a suitcase and you have some 10 items to pack in that suitcase, right? So, and you can't, you know that you're not able to fit all the 10 items in the suitcase, right? So, you want to fit as many things as possible in that suitcase. So, how would you even try to attempt to solve this problem? Can anyone come up with an algorithm to solve this problem? Just the steps of how you would solve this problem. What would you do as classify based on? Okay, so you want to prioritize. You'll prioritize a list. You'll create a list of priority that this is the most important thing. This is less. Okay, so what you are suggesting is basically a greedy approach. So this is a heuristic approach where you prioritize the most important things, and then you just fit in one by one, and then you stop where you can't fit in more things, right? There is a brute force technique to it. Brute force technique is the most trivial technique. I'll use the board to explain it. So, you have, let's simplify this problem to 2 items. So, you have, let's take more, 3 items. So, you have 3 items that you want to fit in a small bag. So, the most trivial solution is 0, 0, 0, which means you are not going to take any item. So, I am representing each binary variable, each item with a binary variable. 0 means that item is not selected, 1 means that item is selected, right? So, let us say I select the first item, this one. So, 0, 0, 1, this is one solution, then 0, 1, 0, this is another solution. So, like this, yes, 1, 0, 0 is another solution, right? So, like this you can go up to 1, 1, 1 where all 3 things are selected and you are able to fit all 3 things, right? So, the number of solutions that are possible here are 8. So, if I had 4 items, then the number of possible solution is 16. If I had 8 items, the number of possible solution is 2 power 8. What is 2 power 8? 256, right? You can see how this scale is growing with the number of variables I have, right? If I have 10 items, how many possible solutions are there? 2 power 10, which is 1024. Now let's increase it a little. Let's say I have 30 items. 30 is not much big, right? 30 is not a big number. You can have bags where you can fit 30 items. You will have come across problems where you want to fit 30 items in a bag if you are shifting your place or something. How many possible solutions are present? What is that number? Any idea? One to 2K giga, meaning 6 zeros. So 1 billion, right? So this solution, only with 30 variables you have 1 billion number of possible solutions, right? If I increase one more, 31, you have 2 billion. If I increase one more, 32 variables, the number of solutions is 4 billion. Just with 30 variables, a very simple problems that we are trying to solve. This is a very classic problem, knapsack problem. So we call this problem a knapsack problem. Just with 32 variables, you have 4 billion solutions possible, right? And if you were to brute force it, it would take maybe minutes or hours to solve this on a classical computer. If you use a greedy approach that you suggested, maybe it will be done within few seconds, right? But even there is a limit to that greedy approach. So it hits limit when you are talking about maybe 1000 variables, right? But 1000 variables is a very small problem. These problems are some of the toy problems that you can use to learn some algorithms or anything, right? So the scale at which we are solving problems is from anywhere between 1 million, I'll just write 1 million, up to it could go to 1 billion or even more than that. this is the scale of just the number of variables. If the number of variables is from 1 million to 1 billion, the number of possible solution is 2 power 1 million to 2 power 1 billion. If you want to comprehend this number, write this number in a calculator and see 2 power 100, just 2 power 100, which is 100 variables, right. So, just this number is equal to more than the number of atoms that are there in the universe, right. So, to solve a problem like this, you can never solve this using a brute force, and even approaches like greedy method, heuristics, local neighborhood search, these kind of problems hit a limit. So, you might get a solution, but you will not always get the optimal solution, right. So, this is where we try to solve problems like that using a solver like this. So, this is a quantum inspired solver, and what this does is basically it checks all the possible solutions that are possible very fast. I'll talk about those use cases. One of the use case is a trunk packing problem. So, trunk packing problem is where you design trunk of the car, and the market value of the car is decided by the volume of the trunk, because if the trunk is too small, nobody is going to buy it. So, if you are planning to buy a Thar for your family, you wouldn't consider it because the trunk size is very small. You would maybe prefer a different car. So, the volume of the trunk decides how much sales of this car is going to happen. So, to estimate the volume of the trunk, what they do is basically they do a brick simulation. How many bricks can you fit in? How many bricks can you fit in? And you can fit in a brick in different orientation and different positions, right. So, you try out all the different possible combinations, and you come up with one value that this is the maximum number of bricks I can fit in. And there is a threshold number that the business decides that okay, it has to fit in at least 400 bricks of 1 liter, only then I am going to approve this trunk design, otherwise not, right. So, in this problem we have hit around 10,000 variables for a small trunk, but then it grows for bigger trunks, and the number of the complexity of this problem, it grows anywhere between 270 million to 500 million. I will tell you what exactly complexity is. For that we have to talk about cubo problems, cubo formulation. So, to solve any combinatorial optimization problem, what we do is we formulate it as a mathematical problem. So, what we you know what, I will cover that after a few minutes. But the idea is we formulate it and then we give it to the solver, and the solver checks most number of solutions, and the solver will use some kind of heuristic. For example, the greedy one that you mentioned, that is also heuristic. So, it will use some kind of heuristic to check as many solutions as possible very fast, and it will not check all the possible solutions because it is not physically possible, practically possible. So, it will check some solutions very fast and then it will give a optimal result, right. So, if you look at this graph, this is basically a graph of cost versus the solution. So, every solution will have some cost or some objective associated to it. For example, if I want to go from here to, let us say airport, right. So, there could be multiple routes that are possible to take. So, these routes can be defined by cost. Right. So, these routes can be defined by cost, right. So, what is the cost of going to the airport if you take each route, and then you plot each route versus the cost. If you take route A, cost is somewhere around 300, route B 600, route C some 200, right. So, you would choose the one with the least cost. Now, the cost function can be defined as a combination of time plus the amount that you are spending, right, because you also want to save on time. So, it can be a multi-objective cost, right. So, this is what is defined here, where you want to minimize the cost, and it just depicts how traditional solvers work. You do not get the minimal cost because the solution space is so vast that you will not be able to explore all the solutions at once. So, what we are trying to do is, for any given problem you arrive at the minimal cost, which is this. And when I say optimization problem, a simple definition from my experience of an optimization problem is whenever you maximize something or minimize something, that is an optimization problem. If you talk about cost, you want to minimize it. If you talk about profits, you want to maximize it. If you talk about distance for a Vehicle routing problem, you want to minimize it. Fuel consumption, you want to minimize it. Number of trucks used to deliver millions of orders per day that Amazon does or Swiggy does, you want to minimize the number of trucks so that your operational cost is reduced. All these kind of problems where you want to minimize something or maximize something. If you talk about portfolio optimization, you want to maximize your returns, minimize the risk. All these problems are optimization problems where you want to minimize or maximize something, and the problem is that there are so many possible solutions that you will not find a solution with the minimum value or the maximum value that you are trying to find. So you have to settle for a suboptimal result. So this is the challenge that we are trying to address. Today we are getting suboptimal results. How do we achieve the most optimal result with minimum compute and minimum energy resources required? Yeah. So this product, it supports quantum computer as a backend. It can support CPU as a backend. It can support GPU as a backend as well. Yeah, so there are two things. One is, in today's world, quantum computers, there has been no paper published for solving a real world problem at large scale. For small scale, of course, you can solve. For large scale, there has not been a single paper published of being solved. The reason, because you have qubits. Qubits have errors in them. When you measure a qubit, you also measure some error, right? So you do not have error corrected qubits today, but recently there was an announcement from Google Willow that they have created an error corrected logical qubit. So basically they combine physical qubits into one logical qubit which is error corrected. So that's how you achieve error corrected qubits. So they have got one error corrected qubit. Their goal is to achieve up to 100 error corrected qubits, and our team is also working aggressively on error correction. So once you have error corrected qubits, to solve problems at this scale, you will require somewhere around 10,000 qubits to 1 million qubits. So if you have 10,000 to 1 million qubits, you will be able to, error corrected qubits, you will be able to solve these kind of real world problems. Today what we have is a 25 qubit physical qubits. So these physical qubits will of course have errors. These will be useful for some of the algorithms, for example VQE, variational quantum eigensolvers, and some other QML applications, because so particularly VQE, because VQE is agnostic of errors. You can still run a VQE algorithm even though you have errors. We can discuss later why exactly VQE runs very well even on error prone quantum computers. But yeah, to solve these kind of optimization problems, you require a quantum computer with error corrected qubits and with at least 10,000 qubits. That's the goal. Sorry? No, error correction we do classically. See, it's a chicken egg problem. Which came first, chicken or the egg? To build a quantum computer, you have to solve an optimization problem. So that problem is called qubit mapping problem, and also error correction is also an optimization problem. And you are building up a quantum computer to solve optimization problems. Sorry? Yeah. So error correction is done classically. We don't use a quantum computer to error correct. Error correction is done classically so that quantum computer behaves without errors. Right. Again, as I said, it's a chicken egg problem. To build a quantum computer, you have to solve certain optimization problems, but these optimization problems are not at a very large scale that these are unsolvable. These are still solvable problems. Okay. All right, I want to make this session a little more interactive. So I would like to ask you, what does the future look like for you? When you hear about quantum computing, AI, and all the latest technologies that are coming up, what does the future look like for you? I understand it's lunch time, but sorry? Unpredictable. Good, in a good way or in a bad way? Okay. Fine. Okay. Efficiency. Right. Right. Yeah. Great. And revolutionize. Right. 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 So the future is unpredictable. We want it to be efficient and revolutionary. Yeah, great answers. I think some of them I have already listed down. More efficient, faster, optimal. But as a civilization, our goal is to make a sustainable future. And I think it's part of efficiency as well. And of course, arriving at sustainability is a revolution. If you arrive at sustainable systems where you do not harm other systems or the ecosystem for the civilization to grow, that is when we have achieved sustainability, right? Coming to some technical aspects, what do you mean by computing? If I want to understand quantum computing, what exactly is computing? Processing and storing. So you store the data, you process the data, and right. The very processing and storing are of course right answers. If you want to boil it down to the core, if you know how to count, if you know how to add, if you know how to solve problems, again processing is part of solving. So that is basically computing, right? And what I want to ask is quantum computing the same, right? No, I might have skipped the slide. Okay, anyway. Is quantum computing the same? Well, technically yes. All you are doing is adding numbers, you are counting, and you are solving. So quantum computing is just a subset of computation, right? And I'll not cover deep into what exactly computation means and what exactly information processing and information systems mean. But quantum computing, this is what you are doing. It's just that the way you are doing it is different. And again, I'll not talk about how exactly it is done because that's a really long lecture. I can suggest some books on this. If you want to really study quantum computing, I would suggest Nielsen and Chong. So Nielsen and Chong's information processing, and I think the name of the book is Quantum Information Processing, right? So I would suggest that book. What makes quantum computing so special? What is the hype all about? We talked about the problems. We know that these problems are very tough to solve. But what does quantum computing have to do with all of that? Right? Yeah, so it is faster for some problems. For some very specific kind of problems, it is faster. And combinatorial problems is one of them. And this is one of the major area where we want to solve these problems, because if you look at any industry, all of them have addressed this problem at some or other point. If you look at production planning, you have some n different machines and m different workers, and how do you schedule these workers to work on the machine so that there is no idle time of the machines and you use the workers' time more efficiently, right? So this is an optimization problem. If you have millions of orders coming in, how do you assign trucks to those orders, and how do you assign routes to each truck? Again, an optimization problem. In drug discovery, in protein folding, if you have 1 lakh rupees, how do you invest your 1 lakh rupees in certain stocks so that you maximize your returns and minimize your risk? Again, an optimization problem. So there are number of optimization problems that I can list, and these are problems that belong to a class called NP hard problems, right? I'll tell what is P and NP. So P problems are basically problems that can be solved in polynomial time, right? If you ask a question, can I reach from this point to airport in 30 minutes? This is a simple yes or no question, that either the answer is yes, you can reach, or the answer is no, you cannot reach. So this is a polynomial problem. Actually, this is not. Google Maps has made it easy because they have implemented some advanced algorithms to solve this problem, but at a low scale this is still a P problem. Basically means whether you can answer a question in polynomial time, right. It could be time complexity of n, like you have to do a step n times, or n square you have to do a step n square times. There are some problems that cannot be answered in polynomial time. These are called non-deterministic polynomial problems. So these problems today we cannot answer is NP. We are not saying that they are not polynomial. We are just saying that we don't know if they are polynomial or not. So today we don't have a polynomial algorithm. Tomorrow if someone comes up with a polynomial algorithm and says, I found a polynomial algorithm to answer this question in polynomial time, then all the problems of that class becomes polynomial. Basically you can boil down every problem into every other problem and you can solve that. So this is what is NP, and NP hard means some of the hardest problems in NP, right. And we can list down the problems that we are trying to solve that are NP hard, but knapsack that I mentioned earlier, that is NP hard. Vehicle routing, vehicle scheduling, portfolio optimization, all these problems come under NP hard, right. And these class of NP hard problems, they can be solved very efficiently with a quantum computer. This is that's all the hype about quantum computing. There are some problems that bring in a great market value for people who are trying to solve those problems, and that is why quantum computers are so important in today's world, right. Again, a very basic question: can you make a PPT on a quantum computer faster? Right? No, it doesn't make sense. You use your laptop to do it, right? So quantum computers are meant for very specific problems, which are NP hard problems that we discussed. There are some other problems as well that you can solve with quantum computers. You can basically use a quantum computer as a node in your machine learning algorithm. So there are parameters in quantum computers that can be trained. So these trainable parameters can act as a node in your machine learning pipeline. So therefore you can use it in VQE and QML applications. But yeah, today we are going to talk more about these problems. So yeah, that's what I tried to explain. Can it solve a complex combinatorial problem faster? The answer is yes, right, if you can formulate it. Again, these are some of the examples of combinatorial problems. What do I mean by combinatorial problems? There are different combinations of solutions possible. That's all I mean by combinatorial problem. For example, when I have to fit in my clothes or my things in a suitcase, I can fit it in different combinations, right. I can select one, I can reject one, I can select one. That's all that means by a combinatorial problem. So some of the examples of combinatorial problems are maps, right. So there are different combinations of routes that you can take to reach from point A to point B. Groceries finds the best order of visiting shops. What's the order of visiting shop? If you go to market, you will plan accordingly, right. So there can be different combinations in which you can visit shops, but you would choose the one that is most optimal for you, that will burn the less fuel and also saves time for you, right. Packing we discussed. Delivery, timetables, airlines, all of these are different combinatorial optimization problems. And again, when we try to solve these problems, we want to find the best route, right. We want to find the best route. We want to find the best order of packing things. We want to find the best path for drivers to drop packages. We want to find the best schedule for classes or trains. And airlines, we want to find the best way to assign crew to flights, right. So what do I mean by best when I say best here? What do I mean by best? Can you quantify best? Right, to organize, and also it depends on the use case. So what do I mean by best? How do I quantify it, right? When I, yeah. Yeah. So coming to your question, there are some problems that are simpler to solve using classical methods, and as an engineer I would never say that you should use quantum computer for all the problems that are out there. Some of the problems like Google Maps have already solved, finding the best route. Amazon has solved delivery problem, and it might not be optimal because no solver guarantees optimality, not even quantum computer, they don't guarantee optimality, but they will arrive at a solution that is good enough, that you know what, I can save a lot of money with this solution, I don't need to keep finding for better solution, right? So runtime also, so like Google and Amazon, they have solved these problems for these specific problems, but there are some problems that are still unsolved. For example, in material simulation, if I had an algorithm that can give me any material that I want, basically I define the properties, this is the property of the material, it should not break, it should bend how much ever I want to bend, it should be transparent, then building Gorilla Glass for mobile phones would have been very easier than it was, right? So there is no particular algorithm that can solve problems like these. It gets solved over decades and decades of research. So there are some problems that are still unsolved, and there is still a scope for solving them. For example, if you take in logistics and supply chain, there is still one problem that is still highly unsolved and unorganized in terms of market, that is stowage planning. So stowage planning basically means you have a ship and you want to send that ship from port A to port B to port C, let's say from Chennai to Mumbai, and then it goes to Africa and then to South America. So if you want to send it, at each port you are going to load some items and unload some items. And then again when you go to the next port, you have to load some item, unload some item. And you have to make sure that at the previous ports, you have to load and unload items so that at the next port when you go, you spend very less time in loading and unloading. Because if I want to unload an item at point B and I have put it at the end at point A, then I have to take out everything, unload it, and then put back everything and then load some extra items at point B, right? So if you take a lot of time in loading and unloading, what happens is you are late for your delivery. And if you are late for your delivery, you have to basically run the ship faster. And when you run it faster, you burn more fuel. And there could be times where your cost of operation would be much higher than the profits and margin that you are making. So this problem is still unsolved, and there are some of the clients that have approached to us to solve this problem for them. So the market is still unorganized. Some of the big tech companies like Amazon and others, they have solved these problems, but there are markets, smaller markets, that still are very unorganized and still operating at a very suboptimal result. This is one, and the other is there are some problems that cannot be solved with current classical compute, like material simulation, drug discovery. These are very difficult to solve. Yeah. Right. Again, coming back to what do I mean by best, right? Best route, best temperature, best combination. If I want to quantify it, I would replace it with the word optimal, right? So when I say optimal, you might have studied some optimization course or anything, even in your like 10th or 11th class. So basically, whenever you define a problem, an optimization problem, you define an objective. This is the objective I want to achieve. So objective, let's take let's take the knapsack problem. I want to fit in as many things as possible, right, in the suitcase. So your objective is to maximize the number of items. This is your objective, right? And you add constraints to it. Constraint is the container should not overflow. If the container overflows, then you can't close it, you can't carry it. The container should not overflow. Also, there could be another constraint. If you are traveling by flight, you have a weight capacity of 14 kg, right? So your volume is a constraint and your weight capacity is also a constraint. So you define the objective, you define the constraints, and based on this objective is to maximize the number of things, constraints is weight and volume capacity. Based on these things, you quantify what is the best. Any given solution, how does it contribute to the objective? For example, I can say, okay, I want to make sure that I don't violate volume constraint or weight constraint, so I will not take anything. I will just take an empty bag, right? So this is a solution, but it is not contributing to the objective of the solution. The objective is to have as many things as possible. So the objective here is 0. If I take 5 things, then my objective could be 5. So this is how we can quantify in terms of objective and constraints, right. Again, coming to the question of why are optimization problems challenging? Why is it challenging? Well, the answer is they are not challenging at small scale. At small scale, you will arrive at the most optimal result even with brute force. If I have 10 variables in the knapsack problem, I can arrive at the most optimal solution but just by checking all possible solutions, right. I can do that. At 10 variables, it is not a challenge. At 30 variables, it becomes a bit challenging. At 1000 to 10,000 variables, it becomes almost impossible. If you try to solve knapsack problem for 10,000 variables with brute force on your laptop, it will run forever, it will never stop, because the number is so huge and your clock speed is not that high, so that you can solve it within real time. So it will run forever for 10,000 variables. So you have to come up with some greedy approach that you sort it in the list of priority and then solve it, right. Right. The answer is intractable. So what I said for 10,000 variables, it is intractable. Like you don't know when it is going to end. It will keep on going for 10,000 variables. And there are classical computational limits. For example, the clock speed. If the clock speed was much higher, then maybe it was possible, but it is not, because there are physical limitations to achieving higher clock speeds. And the number of cores you have, basically number of vCPUs or number of computational units that you have. So there is a limit to it, and that is why these problems are challenging. So this basically calls for, we have hit the limit. We are at a time where Moore's law is dying basically, because if you keep making transistors smaller and smaller, they start displaying quantum phenomena. So they are no more classical, their behavior is quantum. So this calls for a need to build quantum computers. You want to build quantum computers that work at quantum scale, so that you can also control them and you know what is the behavior and you can solve certain problems using those chips. So it is not just that we want quantum computers, but we have hit the physical limit of building smaller and smaller transistors. You have to build quantum computers. Right. So I will stop for questions. This is just a slide of some of the use cases that are there in different industries, automotive being one, manufacturing, O&G, energy materials, drugs and pharma discovery, power grid and infrastructure, transportation and smart cities, aerospace, defense, financial services, logistics. So I'll just stop here for questions. If anybody has any questions or comments, we can take that. Quantum computer. So quantum computer today, as I said, it's used for research. So research institutes and firms that have very big R&D departments with a very big budget for R&D. So these are the people who are using quantum computer today.
At a personal level, if somebody is doing research also, device they are making, how can it be useful cost-wise as well as perfect?
I didn't get the question.
Someone is making some device
Okay.
on personal, like a cognitive load base, to analyze the cognitive load on a person, those who are going for fighter, for army purpose. So for that person, how can a quantum useful? Because he is a one, like just say it innovation stage.
Again, as I said, the quantum computers that are there in today's world, they are not really useful for any applications in today. These quantum computers are being built for future. So what we have today, we can use it for research. We can basically find new algorithms to solve problems in a different way. The only day when the quantum computers are going to be useful is when you have error corrected qubits and you have millions of them. That is the day when quantum computers are going to be useful. So today what people are doing is people are taking access to quantum computer and they are developing their research on quantum computer. They are finding people are contributing to error correction. How can you correct error? People are using quantum computers for VQE applications. VQE applications do not need to have error corrected qubits because it's error agnostic. Optimization applications require error corrected qubits. So today there is no significance of quantum computers in terms of optimization. The significance of quantum computers in terms of optimization is you have a class of algorithms called quantum inspired optimization algorithms. In a quantum computer you have basically you solve optimization problems with quantum annealing, and there is a quantum inspired optimization algorithm that is basically counterpart of quantum annealing that you can run on classical systems, that is simulated annealing. These are the kind of heuristic methods that are being used today to solve optimization problems.
So presently that won't be useful for like defense related projects or some.
If they want to do research, it will be useful. But if they want
So I'm
to
talking
build
about
a
some
use
confidential
case,
project. Actually, it's a brain waves based some cognitive load we are doing. So based on that, we are able to do it with the normal AI methods. So what if I implement or integrate this quantum computer? What I will achieve, compared to the classical ways we are using?
yeah, that's what I'm saying. Today, if I want to compare quantum computer, it will be like comparing the huge IBM machine that was built in the earlier days, the computer, with today's digital calculator that we have, right? So that is the comparison today. So quantum computers that we have built today, these are for research, and these are not error corrected. We are in the NISQ era, which is noisy intermediate state quantum computers.
You have other facilities like anybody can use it or maybe check it like how it works, because the simulators will not give you the exact feel of the quantum.
Yes. So see, simulators will give you the exact feel of the quantum computer. I'll come back to that later. Today that we have the quantum computer, it is usable. People use it outside of the company. They buy the time for the quantum computer. They use it. They do it for their research. If I want to build a new algorithm on a quantum computer and I want to test it, I will use a quantum computer and test it, right? And I can contribute in error correction. I can use quantum computer for my VQA applications. I can use a quantum computer for my what do you call network applications. For example, you have something called as I forgot the name, quantum teleportation. So quantum teleportation, these kind of applications, if I am building, it's definitely useful. And also quantum teleportation has been demonstrated. I think it's been demonstrated by IIT Delhi as well in India,
Yeah.
IIT Delhi and DRDO. So quantum teleportation is a real use case. So that you can still use for defense. But if I am talking only about optimization, that is still in its baby steps. Yeah.
Thank you, sir.
To run VQE, so to tolerate the errors. So what is the demand of T2 and gate fidelity that you are achieving?
Okay, I'll tell you. I mean, I don't have a specific answer to it, but since you mentioned T2, I'll just explain what these terms are. And I mean, of course, there is a limit. If the T2 is very low, then you can't do anything. So there is some standard T1, T2
With
that
respect to your hardware, related to your hardware, 25 qubits.
No, if I want to run VQE, if I use a hardware that has very low T1, T2 rates, then you will not be able to run anything. So there is a threshold that is there that has to be minimum T1, T2 should be this much. I don't know what is that minimum threshold. Maybe somebody else from our team can answer. But since you brought up T1, T2, I'll just explain what exactly it is so that everyone is aware of it. So let's say I have a transistor, right? And it can be either 0 or 1, right? Now I'll just demonstrate it with a bulb. So let's say this bulb is your transistor. If it's glowing, it's 1. If it's not glowing, it's 0. So in a classical computer, when you turn this bulb on, it will remain on, right? It will remain on for 1 hour, 2 hours, 10 hours. For how much time you want it to be on, it will be on. Only when you turn it off, it will turn off. The problem with quantum computers is, so a qubit is, I can represent it with a block sphere, and this direction, this is 0, and this direction, it is 1. Okay. So the ground state of the quantum computer, we will initialize it to 0. Okay. Now if I want to turn it on, basically I want it to point to 1, right? So when I point it to 1, if I leave it for few seconds or few microseconds, it's not going to stay here. So it's going to come down. It's going to come down slowly. So this is a T1 time, right? So this we call as T1 time, right? So because it's not going to stay here, it's going to come down. So whatever operation you want to do and whatever measurement you want to do, you will do it before it comes down too much. Maybe you will do it before it comes here. So this is the error we are talking about. This is the error correction that people are working on. So whatever operation or measurement you want to do, you will do it before it comes down too much or before it degrades too much. So the specific scientific terms is decoherence and dephasing, right? So this, what I am telling is decoherence. Then there is, since we have a quantum computer, we are not limited to zeros and ones. We can have a superposition. Superposition meaning it's pointing somewhere at the center, like horizontally, right? So let's say I have initialized it in this direction. I think this is the plus state. We call it the plus state. This is the minus. Again, this I can call 1, this I can call 0. I could be wrong in the nomenclature, but this is how it is represented. Now if I initialize a qubit to plus state, it will not stay in plus state. It might rotate to minus and then come back. So this rotation we call as T2 time. So you have to do any measurement and operation before it goes off from the state that you initialized. So compared to classical, if you turn it on, it will be always on. If you turn it off, it will be always off. But in a quantum computer, it's very difficult to control this. That if you initialize a state, it might just go down or it might just rotate. So this is called dephasing, and then going down, it's called decoherence. So the higher T1 and T2 times you have, the higher it is, the better it is. Meaning your quantum computer is stable. There are no errors in your quantum computer. Whatever state you initialize, you measure the same. Right? So this is the problem that we are trying to solve today. And what your question was basically, is there a minimum T1, T2 threshold to run VQE algorithm? Yeah. So, yeah, right. So in today, the T1 and T2 are in microseconds. These are in the order of microseconds, like 90 microseconds, 30 microseconds. You can check any quantum computer in the world. They will have their website. They would have displayed their T1 and T2 time. So the higher it is, the better it is. I don't know the answer to your question, what is the minimum T1, T2 time for the chip to be usable. So I can come back to you, or you can find out about it. But yeah, definitely, if this is going to be in nanoseconds or lower than that, then it's definitely not useful, because you cannot do any operations in that time scale. So if it's in microsecond, like let's say it's 100 microseconds, T1 is 100 microseconds, and every time you do an operation, you take 1 microsecond time. So the maximum number of operations you can do on this quantum computer is somewhere between 50 to 100. You can't do anything more than that, because if you try to do more operations, then it will take more time, and by that time your state has degraded, and you will be doing operations on some other state that you don't know what it is. So that's how this works. Yeah.
Is there any drug targeting to the specific body conditions of the human? Targeting the drug, particular specific drugs, pharmaceutical drugs?
Yeah, again, that's an optimization problem, right? So a targeting drug for any conditions in the human body is an optimization problem. How? I'll tell you. You have, I mean, I'm not an expert in this. I can just tell from what I know. So you have a candidate set, okay? You have a candidate set of drug A, B, C, D, E, F, something like this, okay? And let's say you have built a simulator. So some simulator of the condition, that basically what this does is, given drug A plus the condition that you have, it will basically give you the output of how does this condition evolve with drug A, how does this condition change with drug A, right? So this is the simulator you have, right? So basically what it is going to give is a score. It's going to give a score for your drug. If A works very well, it will receive a score of, let's say, 90. If B is very bad, then it will receive a score of, let's say, 60. Or some drugs can receive a score of 30, right? So you have candidates of drugs, and this is going to give you the output of each drug. Now this candidate, it could grow very large. This is the list of variables that you have. So it could grow very vast, right? So you are not going to check each and every candidate with this simulator because that will take a really long time. Again, that would be a brute force method, right? So what you could do is, you can use a greedy approach to solve this. You have something like drug A, and drug A is related to drug B, and then drug B is very closely related to drug D, and something like this. You have a graph of relations of drug. Like basically you mutate one particular bond or of the drug, and you get a new vehicle, and you can get a graph of it. So if drug A is performing good, then you will only explore the graph around the drug A, like a local neighborhood. Sorry? So trial, see, human trials are done only after you are sure that it will work. We cannot do random trials. Like if there is a random drug that we don't know how it will react to condition, you cannot do human trials. Human trials are only done when you have a small subset of drugs, that these are the small subset of drugs that could work on humans, only then you do human trials. So you, from a very long list of candidates, you select a small subset, only then you do human trials. But then again, I am not expert on this subject, so I could be very wrong. No. I just gave the example of greedy approach. There are different approaches like simulated annealing, greedy approach, local neighborhood search. Then there are MILP solvers. If you formulate this problem as a integer linear programming problem or mixed integer linear programming problem, you can use those solvers as well. Guess the answers. That guessing the answers itself is a problem. It's an optimization problem. Guessing the answers is also an optimization problem. You can use different techniques. There are so many papers published for that. Yeah.
Thank you very much, sir. I would like to thank Dr. Amit Kumar Chavan, sir, and Dr. Sagar Darling for delivering technical sessions. On behalf of KST and on behalf of all the delegates present here, grateful to you and hearty thanks to you, sir. We would like to collaborate with you in future also for our outreaching programs. Thank you one and all. We will be having now a quick lunch break after 30 minutes. The interested, those who have given the names to visit the Q labs, they can visit the labs. Okay. Thank you very much.
Oh, this is not. Oh, Allah, Nandalla. Sorry. Okay. ಒಂದು C type ಇದೆ. Okay. HP Lenovo.